All right, so let's just talk about what a parametric equation is. A parametric equation is an equation that is used to define relationships between equations. Okay, so what's happening is you have two separate equations that are somehow related to each other. Okay, and we are going to relate them to each other specifically on a graph quite often. Okay, and typically what happens is that those two functions are related to some other variable. Okay, so there's not just an x and a y. There's a third variable that x and y are both related to on their own. Okay, so if we're looking at an example, let's say you're on a beach and you have some numbers for sunscreen sales and ice cream sales. Okay, this is going to be our two different variables. So sunscreen sales start at 0 for this month here, and then as the months continue, the number of sales changes. Same for ice cream. Okay, now, you should be able to see that these two are related to each other. Look, both of these months, or this month, they're both 0. 3 and 4, okay, 0. This one's 4, this one's 16, so they both got higher, but there's a difference. Oh, but look, they're going up. Oh, they're still going up, and they're back down. Okay, so these two are related to each other. They're directly proportional to each other. But something's going on. I mean, we should know that the sunscreen sales do not affect ice cream sales, right? And ice cream sales do not affect sunscreen sales. There's something else that's affecting both of these in the same way. So we don't really, if you're trying to decide which one's independent and which one's dependent, you don't really know because one of these does not depend on the other. But what do they both depend on? They depend on the temperature outside, right? If it's hot outside, you're going to have to buy some sunscreen if you forgot it. And you definitely are going to want some ice cream because you're going to want to cool off. So that's the idea. So these two are related to each other. Sunscreen and ice cream are related to each other, but they're not related to each other for some, profound reason, just these two. If you include the other variable, if you include temperature, aha, now we see why these two are related to each other because they're both related to temperature, okay? It's very similar to that. So what you have is you always have two equations. And so your y equation would be equal to f of t, so that's some function with a t as your variable. And your x equation would be equal to g of t. It's again some other function. I mean, it doesn't have to be some other function, but it's usually a different function with, again, t as your variable. So typically we work with Cartesian coordinates, so that would be like y is equal to x squared. Notice this is just one equation, right, with the two variables. But when you are looking at it as a parametric equation, it now looks like this, which I know looks more complicated, okay? That makes sense, but sometimes it's just more useful, right? Like the sunscreen example. It's more useful to know what they're really related to, what's really the independent and dependent variable, instead of just trying to relate the two in its own function. Sometimes this is much more useful. Also, the parametric equations can be really useful for finding things like when something happens, or how fast it happens, or just different kinds of things. And they also give you different domain restrictions naturally, which can be very useful, which we'll see later in this lesson. Okay, this graphing calculator thing we might do in class, but it is not necessary. All right, so when we're talking about parametric equations, if we want to represent the position of a point on a curve, both horizontally and vertically, as a function of time, okay, it's not always time, but we're mostly going to use time here. We'll call it t. So we're going to sketch the graph of a parametric curve. How do we do this? The very first thing you need to do is make a table. Okay, the table's really going to help you see what all your x values are, what all your y values are, and where they should go at what time. So that's really going to be helping you out there. Once you have a table, you're going to have all of your points. You're going to plot those points, and then you're going to draw, you're going to connect them. But you cannot just connect them. You cannot just put points on a graph and connect them. You have to include t somehow. How do we do that? We include t as showing what direction it's going in. And you'll see what I mean on this first example. Let's try one out. All right, this says for each of the following, sketch the curve without a calculator, then convert the equation from parametric form to rectangular form. All right, so let's go ahead and try that out. So first thing I'm going to do is I'm going to make the table. So the table is always going to have three variables on it. It's going to have my time, it's going to have my x value, and it's going to have my y value. Okay, so for time, you just need to choose some variables. Make sure you're choosing some negative, at least one 0, and some positive. For this one, I'm going to choose -2, -1, 0, 1, and 2. Okay, now here's what we're about to do. So this x of t is an equation for my x values that will go on my graph. And this y of t is an equation for the y values that will end up on my graph. So essentially, if I let t equal -2, I'm going to plug it into my x's, I'm going to plug it into my y's, and that will give me the x and y value for 1 point. Now, so by the time I'm done, I'll have 1, 2, 3, 4, 5 points. I will connect them and then we will see what happens after that. So I'm going to start with my x. So in order to find all of my x of t's, I'm going to plug my t value into my x function. So I'm going to choose my first t value here, 3 minus 2 times -2. This ends up to be 3 plus 4, so that is 7. Let's do another, -1. This ends up being 3 plus 2, which is 5. Let's do another 0. This ends up being 3 minus 0, which is 3. Now I'm going to move on to 1. And I'm just plugging these t values into my function. 3 minus 2 is 1. Positive 2. This ends up being 3 minus 4, which is -1. Okay, so these are all of my x values that I'm going to use. Let's do my y values next. So now I'm going to plug them all into this function here. So again, first I'm going to start with -2. So I'm going to have 2 plus 3 times -2. So this is going to be 2 minus 6, which is -4. Now I'm going to plug in -1. 2 minus 3 is -1. 2 plus 0 is 2. 2 plus 3 is 5. 2 plus 6 is 8. Okay, so here are all of my x and all of my y values. So now what's going to happen is these are going to become ordered pairs. So my first point is going to be, and you don't have to always do this, I'm just going to show it for this first example. It's going to be 7, -4. That's going to be the point I plot. So I'm going to go over here to +7, down to -4, and that's my first point. Okay, next one is going to be 5, -1. Again, I'm just taking my x's and my y's to create new points. 5, -1. Next one is 3, 2. Next one is 1, +5. And you might be thinking, did I have to do all of these points? -1, 8. No, you don't have to do all these points for every example, but again, I would have at least a couple negative, at least a couple positive, and 1 0. So here, yeah, we really needed all of these. Sometimes it works out where you don't, but try to do as much as you, well, really just as much as you need to be as accurate as possible. You need to have at least the right shape. Okay, so as you can see, this is kind of a line. I don't like that line. I need to make it a little bit straighter here. So we have a linear line here, and that's important to keep in mind that while you do have two equations, the graph should look like just another old function, maybe with some weird domain restrictions, but other than that, it should be pretty normal. Okay, and now I need to do my final piece, that adding the direction that we talked about earlier. So what's going to happen, I'm going to think about what was my first t-value. My first t-value was -2. And always go from least t-value to greatest t-value. Least t-value to greatest t-value. So I'm starting at -2. Well, what point did -2 give me? It gave me 7, -4. This point right here. Okay, and then I'm going to go to greatest t-value all the way to +2. And what point did that give me? It gave me -1/8 right here. Okay, so what happened if I go from least t-value to greatest t-value? That means I went from this point here to this point here. So my direction is starting here and going this way. So my direction is going to make a little arrow that goes this way. And try to put more than one, just a few will be fine, but more than one typically, especially if you have a different shape like an ellipse or something like that, you're going to want more than one arrow. But it looks like this. So this is our final product. You don't need arrows on the end. In fact, you probably should not put arrows on the end, because think about it this way. If I were to put arrows on the end right here, it's kind of like conflicting information, right? Is it going this way or is it going this way? And I know you can tell, but it's conflicting information. We don't like to put conflicting information in our answers. So there should be no arrows at the ends of your graph, just arrows in the middle pointing to the correct direction. All right, let's try another. Okay, so when we do this problem here, let's go ahead and make the table. And I'm going to go quicker this time. That's probably the one I'm going to spend the most time on. T, X, and Y. Okay, see, I'm going to go much quicker this time. And I will say, this is all your chart needs to look like. You don't have to show where you plugged every little step in. That's fine. I'm again going to do -2, -1, 0, 1, and 2. Make this a little bit longer here. All right, so again, first thing I do is plug my t-value into my x function. That's going to give me my x of t. So plugging -2 here, we end up with 4 minus 4, which is 0. Next one, -1. Plug that in. -1 squared is 1. Minus 4 is -3. Next one, 0. 0 squared is 0. Minus 4 is -4. Next one, 1. Plug in 1. 1 squared is 1. Minus 4 is -3. 2. Plug 2 in. I end up with 4 minus 4 again, which is 0. All right, next is y value. So y value is just my t value divided by 2. So I'm going to take -2, divide that by 2, that's -1. -1 divided by 2. 0 divided by 2. 1 divided by 2. 2 divided by 2. Okay, so my points are going to be 0, -1, -3, -1/2, -4, 0, -3, +1/2, 0, 1. So let's go ahead and plop them down. So 0, -1. Right there. Next one, -3, -1/2. Next one, -4, 0. Next one, -3, +1/2. Next one, 0, +1. Okay, so now I'm going to kind of connect the dots here. Okay, sorry, it's not perfect. It's kind of hard to draw on this. But so that is my, and what is this? It's a sideways parabola, right? It's a sideways parabola. So finally, my last step, I'm going to go ahead and put the direction on here. So again, my first t value gave me the point 0, -1. My last t value gave me the point 0, 1. Again, always go from least t value to greatest t value. So what direction is it going in? It's going from here all the way around to here. So that will be my direction. Again, do not put arrows on the end. Let's try another. All right, so let's start it again. First thing you need to do is make your table. And that's what you do pretty much anytime you've got the parametric equation and you're wanting to make a graph. It's always our step here. All right, so again, I'm going to choose some t-values. Now I'm going to choose different t-values this time just because this is well, these parametric equations are, ooh, whoops. These parametric equations, what are they? They're cosine and sine. So I'm not going to choose difficult t-values. I mean, if you get to choose whatever t-values you want, make them nice ones, right? So I'm going to go ahead and start with 0 and go all the way to 2 pi. That should give me actually all the possible values because those are all, I mean, those aren't all the possible thetas, but that should run through the entire unit circle. So I'm going to go ahead and choose 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, there they are. So let's go ahead and work it now. So I'm going to have x of t. So I'm going to plug 0 into my x function. So I'm going to have 2 times cosine of 0. You should all know cosine of 0 is 1. So 2 times 1 is 2. Pi over 2 makes cosine 0. So this will be 0. Plug in pi. 2 times cosine of pi. Cosine of pi is negative 1, so this becomes negative 2. 3 pi over 2. Plug that in. Cosine of 3 pi over 2 times 2. So what is this? 0. 2 pi should be the same as 0. All right, now let's do the y value. The y value is 3 times sine. So when I plug 0 in a sine, I get 0. So 3 times 0 is 0. Pi over 2 gave me sine 1. So 3 times 1 is 3. Pi makes sine 0. So 3 times 0 is 0. 3 pi over 2 makes sine negative 1. So 3 times negative 1 is negative 3. And then 2 pi, again, will make it 0. All right, so let's go ahead and plot our points. So we have 2, 0. We have 0, 3. We have negative 2, 0. And we have 0, negative 3. And then lo and behold, when I have 0 as my t and when I have 2 pi as my t, I get the same point, 2, 0. That kind of makes sense, right? Because they're going to have the same values on the unit circle. So I'm going to go ahead and connect this, or not connect it. Wow. Let's try that again. Here we go. Okay, still rough, but it's connected now. Here we go. All right, so those are my points. And then finally, I need to add my direction. I'm going to go for my least t value, which I chose was 0. Oh, don't want that. Let's see if I can move it here. I don't, oh gosh. There we go. Okay, so I'm going to choose my direction again. Again, I'm going to go from the least t value to the greatest t value. So I'm going to go from 0 to 2 pi. Well, what was my first point? 2, 0. What was my last point? 2, 0. Ooh, not helpful, right? So instead of going from least to greatest, I'm just going to go least to almost greatest. Okay, I'm just going to go in the right direction. So what was my second to last point I plotted? It was this guy right here. It was 0, negative 3. So I am going from this point around here to this point. Guys, it matters. It matters, okay? I'm not just going from this point to this point, okay? I know I kind of made it look like that, but I went from here to here to here to here and then back to here. So just be careful when you're choosing your direction. It should go in this order. Your t value should go from least to greatest. This is kind of how your t shows up. This is what shows it as a parametric equation and not just some conic section. Now, could you represent this with a conic section? Absolutely. This would be an ellipse, right? So this would be an ellipse. So it would follow the x squared, because its center is at 0, 0, so I don't need x minus h. So it would be x squared over my a squared. What's my a? It's 2, so this would be 4, plus y squared over my b squared. My b is 3, so this would be 9, is equal to 1. So you can see, you should be able to kind of see these equations, and we're going to find out how to do it without graphing them first to kind of help you and make it quicker. But it's the same idea. All right, so now we're going to move on to a different one. Number 2 is kind of more interesting because it's got some different domains, okay? Let's see how these functions can affect our domain. So this first one's pretty normal. If I was in class, I would just let you work on it. So if you want to pause the video here and try it yourself and then check your answer here in just a moment, you can. All right, here's our table. And our values, again, I'm just going to choose some positive, some negative. Plug them in. Oh, x is equal to t. That's odd. That almost makes it not parametric at all. It's still parametric, but it doesn't feel like it because really I could just replace, I mean, what could I do? I could say since x of t is equal to t, I could just plug in x for t. So what is this function going to look like? It's going to look like x squared minus 1. So just a little tidbit of information. Now I'm going to plug these x values, or sorry, now I'm going to plug these t values into my y. So negative 2 in here is going to make it 4 minus 1, which is 3. Negative 1 is going to make it 1 minus 1, which is 0. 0 is going to make it 0 minus 1, which is negative 1. 1 is going to make it 1 minus 1, which is 0. 2 is going to make it 4 minus 1, which is 3. Okay, so now we're going to graph them. So again, I'm going to have the points negative 2, 3, negative 1, 0, 0, negative 1, 1, 0, 2, 3. So I'm going to start at negative 2, positive 3. Then negative 1, 0. And right, if I were to connect these as I go, I could already put my direction down. We won't do that, but you could. 0, negative 1, 1, 0, and 2, 3. And when I connect them, well, what order did I draw them in? I went from this point to this point to this point to this point to this point. So it's going in this direction. Okay, and we also need to go ahead and find the rectangular form. So the rectangular form is the one that relates x directly to y. Okay, it'll have x and y in all one equation instead of two. So here's how that happens. So, and it happens just like I kind of mentioned up here. But if we know that x is equal to t, once I have solved for t, if you have t by itself, you can then plug in whatever is left on the other side for t here. So again, that'll end up being y of t is equal to x squared minus 1. So this ends up being y is equal to x squared minus 1. You'll notice that one doesn't have a different domain. However, this next one does. And I know this next one looks very similar, but it does have a different domain. So let's take a look at it. So again, table. All right, so, and again, I'm going to choose a few. You'll notice that if you choose the right t's, makes your life a lot easier. Again, you want some positive, some negative, and a 0. All right, now I'm going to start plugging them into my x function. And you see something pop up right away that tells you this is going to be a little bit different. Okay, so when I plug them into my x function, what happens? Negative 2, okay, I'm plugging it into my x function, so negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. All right, those are my x values. Notice what's missing. All of these x values are positive, every single one of them. That's going to affect the x values on my graph. And what's the x values on my graph? That's my domain, okay? So what's going to happen is my domain's not going to have any zeros. Well, I'm sorry, it can have zeros, but it won't have any negative values. Okay, so keep that in mind as you're going. All right, next, let's do our y values. So we're going to plug our t's into our y values. Be so very careful. Do not plug these x values in, right? You want to plug in your t values. Just be careful as you move forward. All right, so negative 2 to the 4th minus 1. Okay, so that's going to be 16 minus 1, which is 15. Negative 1 to the 4th minus 1, so it's going to be a positive 1 minus 1, which would be 0. 0 to the 4th minus 1 is negative 1. 1 to the fourth minus 1 is 0 again. And then 2 again will give us 15. Notice, yeah, this does give us one negative. Is it restricted? Absolutely, but ranges are restricted a lot. Ranges are restricted a lot. It's usually domains where you can plug in any number that you want. But again, this one won't have a negative infinity to positive infinity domain. It will be restricted. So let's go ahead and point them. We got 4, 15. And you know what? I'm just going to go ahead and plot this up high in the sky. And then we also have 1, 0. And then we have 0, negative 1. And then we have 1, 0. And then 4, 15 again. So what happened? I started here. I went down. And then I went back up. Ooh, okay, so our direction is happening twice. And that can happen with these restricted domains quite often. I'm going to go ahead and connect the dots here. Now, also a thing to consider is at this point in time when you have a restricted domain, I mean, we know that's going on forever, but this stops here. I will have nothing on this left-hand side of the graph because my x values just can't get there. They have to be positive. So I'll have nothing on that left-hand side of the graph. So the next thing to consider is, will this be an open dot or will it be a closed dot? Well, the question is, can t squared equal 0? Absolutely, so we will include it. So this is going to be a nice firm closed dot there. Okay, then when you're drawing arrows, yes, it does go back, it does do both directions. So I'll kind of signify that as it started down, and then I'll kind of say, then it went back up. Okay, and yeah, that's what it looks like. And so again, this is kind of the situation where both of these functions have infinite domains. So why doesn't this have an infinite domain? Well, what's happening? X squared is equal to t squared. This function t squared has a restricted range, okay? Which means x of t has a restricted range, okay? So what does that mean? That means that this function here can only put out certain values. It can only put out things greater than or equal to 0. So that's going to affect our overall domain because if x of t can only put out 0 or above, our graph will only have x values or only have a domain of 0 or above. Okay, well, all right, and we also need to find the rectangular form for this problem. So again, like we said earlier, you just have to solve for t in your x equation and then plug it into the other. And I mean, technically you can do the same for the other. Especially in this case, it's definitely easier on your x equation. So I'm going to solve for t, and to solve for t, I'm going to square root x. So this is going to end up with t is equal to the square root of x. Once I have that, I can plug it into the next equation. So instead of t in the next equation, I'm going to have the square root of x. Okay, so there's that one. And then there's another way to do it as well. And again, notice, this is not that whole function, right? You guys should know what x squared minus 1 looks like. This is not the whole function. So when you write it out, you also have to say, hey, its domain is whatever this function's range is. If you know x of t's range, you know your new domain. So I'm going to say x is, ooh, whoops, I want to say greater than or equal to. X is greater than or equal to 0. Okay, that's one way to do it. There's another way to do it. Sometimes you can be kind of strategic here and say, well, ooh, this is x, or this is t squared. This is t to the fourth. So y of t, what does it have? Y of t is equal to t squared squared minus 1, right? This is the same thing as t to the fourth. Remember, when you have an exponent to an exponent, you multiply. I haven't changed anything. I'm just taking y of t and rewriting t to the fourth as t squared squared. Well, what do we know t squared is? T squared is x of t. So again, I could rewrite it. And then again, don't forget your domain restriction if there happens to be one. So if you have a range restriction on x of t, you have a domain restriction on your whole function, on your rectangular form. We'll continue now. All right, so on this one, we have x of t is equal to sine of t, and y of t is equal to sine squared t minus 1. Okay, so you might be tempted to do some trig identities or something like that. That's really not necessary for this problem, because when you're just plugging in your functions, um, again, when you're just plugging in your t, it's not going to make a big difference. Just do be aware, remember that sine squared of t is really the entirety of sine t squared. So, I mean, let's just keep that in mind. That's the same thing. So, in fact, if we want to go ahead and make the rectangular form, what will we do? Well, this is sine of t. This is sine of t squared. So, let's replace sine of t with x. And there you go. So this is going to look almost exactly to our previous one, right? It was also x squared minus 1, but it's going to have a different domain restriction. Let's talk about that. So again, how do we get our domain restriction? We go to x and we look at its range. If we know x's range, we know our rectangular domain. So what's the range of sine of t? Well, it has a minimum of -1. It has a maximum of +1. It looks something like this, right? Well, that looks more like cosine, but it starts in the middle. Remember, it starts in the middle, goes up, and comes back down. So it looks similar to this with a maximum of 1 and a minimum of -1, okay? So that's going to be our domain restriction here. So I can even say x is in between -1 and +1 for my domain restriction. And again, in order to find the graph, you just have to find your t values, your x's, and your y's. Make sure for this type of function, since you have sines and all that kind of good stuff, that you use radians for your t values. So again, I would choose 0, pi over 2 pi, 3 pi over 2, and 2 pi to plug into your x's and y's before you graph. And I'm going to have the answer to this one on my website if you would like to check it out. Number 4. Okay, let's try out number 4. Number 4 has x of t and y of t. Again, notice this is e to the t. Notice this is e to the 2 times t, which, by the way, is just e to t squared, right? So that's kind of something to come think about here. So if I wanted to get this into rectangular form, what do I have? I have e to the t squared. Again, whenever you have an exponent to an exponent, you multiply. So what is this really? It's e to the 2 times t, or t times 2, either way. But that's the same thing as e to the t here. So I like it like this because now what can I do? I can say, well, I know what e to the t is. E to the t is x. So instead of saying e to the t, let's say x. Aha. See how this is like the exact same equation? But again, it's going to have a different domain. Okay, well, what's our domain for this one? Well, what was your previous range? If your previous range was e to the t, what's your domain on this one? It's going to be greater than 0. And again, you could do the chart and you could find all of your x and y values, but I know it's going to look like this, so I could almost even kind of draw it in already. But be careful with your domain restriction. This domain restriction says greater than 0. So at 0, it should just be an open circle. So it'll be an open circle here, closed circle here, and then at 415 all the way over here, high in the sky, it'll look like that. Now, that's most of the graph. What are we missing? We're missing our direction, right? So in order to find that, you're probably going to have to do the chart. So you know what? Let's go ahead and do the chart real quick. Okay, so we have t, we have x, and we have y. Again, I'm going to do some negative. Oh, there we go. Drag those down some. And then let's try it out. So to get my x values, I'm going to plug -2 into my x equation right here. So my first thing would be e to the negative 2. And then to get my y values, I will plug them in here. So this would be e to the negative 2 times 2, which is e to the negative 4 minus 1. Here's what I want to mention about this. Is there a negative in our answer? Yes, but it's in the exponent, right? So if I were to rewrite e to the negative 2, that's the same thing as 1 over e squared. Remember, e is about 2 point, oh gosh, I can't remember the decimals right now, but it's about in between 2 and 3. And so what do we really have here? We have 1 over a positive number squared. So overall, this whole thing is positive. And let's think about it. If we choose to keep rising, or if we keep raising our t values, what's going to happen? Or sorry, if we keep lowering our t-values, it'll just get closer and closer to 0. You'll have 1 over e to the 100th or 1 over e to the 1000th or whatever value you plug in. It's just going to get closer and closer to 0. It should never pass it. So that's another thing to consider. That's another way to look at your domain, is think about how you can plug in your t-values and what will come out, okay, which again is your range. That's exactly what we're doing. So it's e to the negative 1, e to the negative 2 minus 1. This is 1, this is 0. Remember, anytime you have a 0 in the exponent, it's a 1. So what is this really? So over here we would have gotten 1 minus 1, which is 0. Then we have negative 1 and 0. Then we have, oh, whoops, that's not right. E and e squared minus 1. And then we have e squared, e to the 4th minus 1. So what's happening? Here, we're really close to those 0 values, okay? And in this one right here, oh, oh yeah, this one right here is really close to 0 minus 1, which would be negative 1. So this point is approximately 0, negative 1. Now, is that perfect? No, it's not. It's just it's going to get closer and closer and closer to that. So that's again why we have an open circle here, because it's never going to reach that 0. Your x is never going to be 0. So it's going to be an open circle here, but it'll get closer and closer and closer to it. But what's really happening? Our lowest t value is starting right next to that point, and then it's going up. So we can kind of create our direction with that. All right, last group of problems here. So this says show that the parametric equations below define a circle. So it wants us to show that this is a circle. So what are we headed towards? We're headed to x minus h squared plus y minus k squared is equal to r squared. Hopefully you remember that from your last test, but that's the equation we are headed towards. So I want to make it look like that. We're pretty far from that right now, right? We have an x and we have a y, and we're going to have to combine them. Well, what did we talk about earlier? Earlier we talked about solving for your t. There is no t here. Well, I mean, you could solve for your theta, but honestly that's going to make things more complicated than it has to be. So instead of thinking about it that way, let's go ahead and solve for just the cosine and the sine parts first, or even just the r cosine, okay? And you're going to see why here in just a moment. So I'm going to take x theta is equal to h plus r cosine of theta. And I'm going to just say this is x is equal to h plus r cosine of theta. And I'm going to solve for r cosine of theta. So I'm going to move over that h, so I'm going to have x minus h is equal to r cosine of theta. And then I'm going to go ahead and square both. And you can call me crazy, but I'm going to show you why it works. I'm going to square both sides, which means this whole thing gets squared and this whole thing gets squared. Okay, let's keep going. Again, you'll see why it works here in just a moment. Let's try the other side. I'm going to do the y side now. So this is y is equal to k plus r sine theta. And again, I'm going to do the same thing. I'm going to move over the k. and I'm going to square both sides. So when I square this whole side, that's what it looks like. When I square this whole side, it'll square both the sine and the r. Okay, so this is what I have right now. Now, let's look at it. What if I add these two together? Because that's what I want, right? I want x minus h squared and y minus k squared to be equal to r squared. So what happens if I add these together? And some of you guys might be going, oh, I see what's happening. But if you don't, that's okay. Let's check it out. So I said this side plus this side is equal to, well, if this is equal to this, and these two are equivalent, the right-hand sides, their sums also must be equal. So this is going to be equal to r squared cosine squared theta plus r squared sine squared theta. Now, here's the cool part. Here's where our dreams become reality. We have the left side of our equation. Can you think of how we get to our right-hand side of our equation? Give you a hint, it's a trig identity. Maybe you can figure out before I put it here. Here's what I'm going to do. I'm going to pull out a greatest common factor of r squared. And you probably already saw, hey, that's cosine squared plus sine squared. And you should know that trig identity. Cosine squared plus sine squared is what? It's 1, right? So we have x minus h squared plus y minus k squared is equal to r squared, and voila, we have reached our circle. All right, excellent. Let's try another. You can see these are a little bit tougher. Here's the next one. X is equal to 3 cosine theta, y is equal to 5 sine theta, and it wants me to show it in rectangular form. And I'm going to tell you, that looks a lot like a circle, right? Those cosines and sines kind of create those shapes, the circle, but also the ellipse. Here's how we know this is the ellipse. Guys, what does this kind of mean? It means that your vertical aspect, your sine, has a radius of 5. And your horizontal aspect, your cosine, has a radius maximum of 3. So we should kind of already be able to tell that this is an ellipse. And when we start putting those pieces together, well, what does that mean? That means I'm headed towards a goal of x squared divided by something plus y squared divided by something is equal to 1. I'm going to tell you what's going to help us out immensely here. It's going to be this trig identity again. Sine squared theta plus cosine squared theta is equal to 1. Here's why this is cool. Because remember, on the right-hand side of the ellipse, I need everything to be equal to 1. So if I can make it equal to sine squared cosine theta, sorry, if I can make it equal to sine squared cosine squared, then voila, I've got my 1 on the right-hand side. So here's what I'm going to find. I'm going to find cosine squared, or I'm going to find cosine and I'm going to square it. I'm going to find sine and I'm going to square it. So what do I have? I'm going to have cosine theta is equal to x over 3. Sine theta is equal to y divided by 5, and I'm going to square both. Remember, you got to square the whole thing whenever you want to do that type of thing. So now I'm going to have cosine squared theta is equal to x squared over 9, and sine squared theta is equal to y squared over 25. All right, hey, this kind of looks like an ellipse with your center at 0, 0, but it looks like it. So I'm going to add them together, see what happens. Well, same thing as before, right? This plus this must be equal to the left-hand side sum. So if you've got the right-hand side sum must be equal to the left-hand side sum. What's your left-hand side sum? It's cosine squared theta plus sine squared theta, which is just 1. So voila, now you have your ellipse, just like you knew you're going to end with. This says x is equal to 4 plus 2 secant theta, and y is equal to 6 plus 3 tangent theta. Alright, this is going to be the same idea, but I'm going to use a different trig identity this time. Here's how I know I'm going to use this trig identity. There's secants, there's tangents. So I'm going to use 1 is equal to secant squared theta minus tangent squared theta. That's the one I'm going to use. All right, and again, I'm going to solve for secant. I'm going to solve for tangent, square them. Oh, whoops. That should be a 6. What am I doing? I'm doing a couple steps at once. I'm saying if I'm solving for secant, what am I going to do? I'm going to move over the 4, then I'm going to divide by 2. So x minus 4 divided by 2. Same here. Move over the 6, then divide by 3. So y minus 6 divided by 3. Then I'm going to square both. You can see it already, right? You can see it already. This is part of my conic section. This is x minus h divided by a squared. This is y minus y minus k squared over b squared. So when I add them together, or really what should I do? I should subtract them because this is what I'm headed towards. So I need the secant squared one minus the tangent squared one. So I'm going to do my secant squared one, which is this guy right here, minus this guy right here. It's going to be x minus 4 squared over 4 minus y minus 6 squared over 9 is equal to secant squared minus tangent squared, which as we discussed is 1. All right, last two examples. It says find a set of parametric equations for the given rectangular equations using t is equal to x plus 1. So essentially, it's giving me a rectangular equation and asking me to find a parametric equation where t is equal to x plus 1. Well, the first thing we can do is if we know t is equal to x plus 1, that means x is equal to t minus 1 if I move over that 1. So bam, that's one of my equations, easily right there. So I have x is equal to t minus 1, and then I need to go find y of t. Well, here's how I do that. Instead of x, I will take its counterpart, t minus 1. So I'm going to say y is equal to 2 minus x, but instead of saying x, I'm going to say what it's equivalent to, the one that includes t, because I'm eventually wanting y of t, and distribute that negative, and x of t. Oh, that should be plus 3, shouldn't it? Yes. Okay, so now I have this guy here, and that's finished. Those are my two parametric equations. Let's try the next one. So again, I already know, because I'm using the same t values before, that x is equal to t minus 1. And now I'm just going to plug that in for x over here and solve for y. So I'm going to say t minus 1 is equal to 3y minus 2. And I'm going to solve for y. So I'm going to add 2 over, divide by 3. And there's my y equation, and here's my x equation. Oh, whoops. T. There we go. T minus 1. All right, and then we'll be all done. All right, that's it for today's notes. I know that they were long. I will say make sure that you understand these parametric equations because they're about half of your test and you need a good basis to really continue on. So if you've got questions, please come in and ask. Please make sure that you're doing the homeworks. So that you can come in and ask me questions. Please do not just watch this video and assume you have a good understanding. Remember, we just cover the basics in the notes, so make sure you're delving deeper in your own homework. All right, have a wonderful day. Hey, if you watched this video, you made it through to the end, good job, and good luck on your homework.